P mu R as a sum of these two terms and plus Ls by root 2 and summation over k not equal to 0. Now here I have alpha mu k minus beta mu k because of this extra minus sign here times e to the power minus I. So this is what we get from our Neumann boundary conditions. But only the first part. We have applied Neumann boundary conditions only at sigma equal to 0, not yet at sigma equal to pi. And out of this, we already derived something. What is the thing that we derived? The left hand side has to be 0, and therefore right hand side also has to be 0. So the only way it can happen is that term by term it is 0. And for this to happen, this should be 0, which means P mu L and P mu R should be same. That is the one. Then this term will drop out if this term can cancel each other. And here, this can drop out if this cancels with this, which means we have the same modes. So it is that is the physical outcome of this condition for this particular case, that alpha mu k turns out to be beta mu k, which means we have the same Fourier modes for the left and right moving waves. This is one thing. And we also have P mu L equal to P mu R. Okay. So these are the two outcomes of this. Now I can leave this last line and I can remove this part. Okay. So we are still taking this and we are discussing this one. So fine. And what is the outcome? If we apply Neumann boundary condition at sigma equal to 0, we find P mu L equal to P mu R and alpha mu K equal to beta mu K. This is the net outcome of our this particular boundary condition, right? When we have applied this boundary condition, this is what should happen, so that then this can cancel this can cancel this, and you have left hand side equal to right hand side, 0 equal to 0. This is one thing. Now, of course, it has some physical meaning. Physical meaning here is that we have the same Fourier modes for left and right moving waves, and P mu L equal to P mu R simply implies that a string cannot bind around itself. P mu L is equal to P mu R. So now we would like to use the other, at the other end we have not yet applied. So we need to apply Neumann boundary condition again, but for now sigma equal to pi. Okay, at the other end of the string, and this might give us additional conditions. And what is that? So what we do is we apply 0 equal to del sigma x mu is del sigma x mu L x sigma equal to pi plus del sigma x mu R, and this also at sigma equal to pi. This is what we want to do. So this then we could write Ls square by 2 P mu L plus ILS by root 2 sigma k not equal to 0, 1 by k alpha mu k, and e to the power minus ik tau plus sigma into minus ik and plus, so this would be the minus ls square by 2 p mu r, and this here it is ILS by square root of 2, but here I should have plus IK as you pointed out, okay, and beta mu k into e to the power minus ik tau minus sigma, and now this whole thing or this whole thing at sigma equals to pi, right? Okay, so here we had this, because of this we had minus, and here we had more minus, and so this is all right. Okay, so this is what we have at the other end, sigma equals to pi. So if we implement it, sigma equals to pi, maybe we can do it here. So this thing goes away and this thing goes away and this thing goes away and this thing goes away. So that's our solution, right?
Sigma equal to pi, that's your...
Have I made some mistake?
Oh, no. It's okay, yeah.
It's okay because this we are still applying this condition. No. Oh, this is the outcome of the other one. This we are applying at sigma equals to pi. Okay. This is at sigma equals to pi, and so we have no, you are right. Let me see. I have made a mistake. This sigma equals to pi and sigma equals to pi. Yes. So let me put this into bracket and let me call it sigma equals to pi. Okay. Now let me do it carefully. How we do it? And here, you see, we can now. So we have to implement three things at sigma equals to pi. And of course, these two additional things, they still hold, which we have derived already. Okay? That P mu L is equal to P mu R, equal to, we can say P mu, and alpha and beta, they are also the same. So what you can do is, so if we take P mu L equal to P mu R, then this term would drop out. 0 plus, now let me take let me keep these factors plus ILS by square root of 2 into, okay, let me keep this also there. Let me just cancel k with k. Okay, let me cancel k with k and let me put alpha equal to beta. So then I would have this and I would have this k not equals to 0. Now I do not have k in the denominator, and this is the factor. Let me take alpha mu k as the common factor from here, and e to the power minus ik tau I can take common, ik tau, let me keep common. So this into this into, now what I would have, this is the same, this and this comes here. So I would have minus I into e to the power minus ik e to the power minus ik tau plus pi, tau is gone, minus ik pi. Okay, and plus this here, so this is plus I times, this is gone, this is, I have put it here, e to the power minus ik, here minus ik into minus pi, so this is plus ik pi. Is this okay? All right, and we could take, let us say, iota outside, then this and this, let me remove. So it is e to the ik pi e to the power, this should then be equal to your 2 iota sin k pi. Is this okay with plus sign or minus sign? This minus this should be plus. Okay?
But it must 2 times I times I. Because
Oh, yeah.
bracket,
Oh, yes.
sorry,
Oh, yes.
you put it out in. No,
So,
if,
yeah, I could take this, if we like, we could keep minus I out here, then this